We have this really cool way of figuring out the concentration of acids and bases, and it is a very common thing to use in chemistry for sure. So this concept of titration is what we're going to talk about today, and I'm going to walk you through the process here. Why don't we do it this way? We're going to start right in with this concept. So we should draw this, and if we have this really long, it's probably about 2 feet tall. We have this glass tube called a buret. Okay, and a buret is probably up here is 0 mLs and down here is 50 mLs. And it's upside down on purpose. Okay, and we clamp it to a large stand called, of all things, a buret stand. So we're going to cut through 50 right here, and we're going to have a base here. Okay, so now there's this nice little base. So this is really, we should probably clamp it so it doesn't fly off of there. Okay, so here's this really tall graduate cylinder, really narrow, but it's tall because it can be very precise now. And we fill it up with some kind of chemical, and in this case, we're going to add, let's say, hydrochloric acid. Right? So we're going to say that we put hydrochloric acid in there. And underneath, we're going to use a Erlenmeyer flask. Now, we can draw those better than that, so let's fill that in maybe. Okay, so there's your Erlenmeyer flask on the bottom. And inside the Erlenmeyer flask, we're going to have sodium hydroxide. Now, acids and bases react and they neutralize, and they form salt and water. Okay, but there's a couple of things we can do to figure out what's the concentration of this unknown. So this process, by slowly adding chemicals, this hydrochloric acid, drip by drip by drip, to this unknown here, that's called titration. All right, so let's go over here and let's look a little more closely at what's going on. Okay, this is a very important concept in chemistry, so definitely worth your time. All right, so what we're going to do is say inside that Erlenmeyer flask is a bunch of sodium hydroxides. Excuse me, so we're going to have OH minus, a whole bunch of them, certainly more than 4. But here's the idea. From the buret come these H pluses, right? Because those react with the OH minuses in the water. Now there's still Na pluses floating in the water, and there's still Cl minuses floating in the water, but all we care about is that H and OH come together. Okay, so let's do that. Every time a hydrogen ion or proton comes down and reacts with this, you get H2O, and that is neutral. And then the next one comes down, and we keep forming H2Os until they're gone. And so now we have no more H2Os. So now if we add one more H plus, right, it becomes acidic. Because now there's nothing else to neutralize that H plus. And so now it's an acidic situation, okay? But let's be a little bit more clever about this. Let's do this again, all right? But this time, let's put our Erlenmeyer flask here, make them a little bigger, okay? So there's Earl. And this time we're going to put something in here called phenolphthalein. H-A-L-E-I-N. And that has to do with a group. There's a group, a chemical group that's called the phenol group, so on. Okay, so here's this stuff called phenolphthalein. When it's in acid conditions, it's colorless. You don't see it. right? But when it's in base conditions, it's actually magenta. That's why I'm using this color pen. It's basically a deep pink, right? It's a very strong pink color. So when it's in base conditions, it turns magenta. And when we switch from acid conditions to base conditions, this purple color shows up. We could call it purple. All right. So what happens? What if we had inside here, what if we had the H pluses in here first, and we added the OHs from the buret? Now we'd have a different situation. Not totally different, but every time that the H and OH get together, right, we form H2O, right? But at this point, with all of these in here, it's still acidic, and so it's still colorless, right? And we keep doing that. Get rid of all the H pluses, and then something interesting happens. Now we have excess OH minus, and when there's just one more OH compared to the H pluses, basically, when there's an extra OH compared to that, when there's an excess and all the H pluses are gone, they're turned into water now. When there's excess, this is basic. When you have basic conditions, you have magenta. And so it's an indicator. It tells us. So phenolphthalein is an indicator. It's a chemical that turns colors under certain conditions. So when we added this hydroxide up here, right, before we did this, this was colorless. That's an acid. H plus is the acid. When we have that in here, even though the phenolphthalein, which is colorless, right, you can't see it in there. But what happens is when we get rid of all those H pluses, then we start adding OH, and there's nothing to counteract that. That's a basic situation. And that chemical phenolphthalein turns from colorless to magenta. And it's very quick and it's very noticeable. And then we stop. We stop adding the chemical. Okay? So that's the idea of a titration. So how does that help us figure out what's going on? All right, so here's your buret. Draw it again. Okay? And let's say that we know now that in this buret we used, let's say, 18.1 mLs of HCl. And we knew that that HCl was 0.15 molar. So we used this portion right here. We went from 0 to 18.1. And then we know that when we had the unknown base, we knew it was a base. Right? We knew it was a base. But let's say that we were testing 12 mLs, 12.0 mLs of sodium hydroxide. How strong do you think that was? Well, we have a way of doing that. First of all, you need to consider this. If you only had 12 mLs of the base, but it took 18 mLs of acid to counteract it, that should be stronger. Doesn't that make sense? Isn't the base stronger? If you only need 12 mLs of that base, but you are adding or counteracting it with 18 mLs of HCl, this stuff is weaker. Excuse me, this is weaker than this, right? You don't need as much of this. And I also want you to see then, always keep your eye on the ratio. Okay? And what ratio do I mean? Well, you know it's going to be weaker. How much weaker? Well, you have two numbers here. You have 12 mLs and 18 mLs, right? Or you could say 18 and 12. Now, which of those two results in a bigger number to make something stronger? This one. This is 1.5. But this one is 6, right? This is basically reduces to 2/3. So this is 0.67. And so we're going to find out that that acid is 1.5 times stronger. Okay, you can do this without even calculating. Let me show you how that works. We already know how to do this. So we take the molarity of the acid and its volume, and it should be equal to the molarity of the base times the volume. Now where do I come from to say that? The moles of the acid equal the moles of the base when that indicator turned color. You see right here, when that magenta first shows up, we know to stop adding the acid. Because we said it's neutralized. As soon as you see magenta, then you'd say, oh, boom, we're done. We have base, or we have not acidic. Right at that point, that last drop is so exact that we have exactly the same number of moles of acid and base. Okay, so we're saying moles equals moles. But we want to know how strong is that acid. I'm sorry, how strong is that base? This right here, we're looking for this. How strong is that base in there? Well, we've done this before. Molarity of the base. Leave this here, but divide by that volume of the base that you used. And you see that VA over VB? Watch what happens. We're now going to substitute our numbers. The molarity of the acid, was 0.15 molar. The volume of the acid, that volume was 18 mLs. 18.1 mLs, and the base that was in there was 12, right? That's 12. Do you see this? This is your 1.5 times, right? I'm not going to calculate it. That's 1.5 of 15, which is about 21 or 22, 0.22 molar or so. Okay, so that's how you do it. That's how we find the concentration of what's in the unknown. Okay, we should probably do another one. A very good example. And it's definitely worth the practice. Okay, so this time we're going to draw the buret over here. And we're going to put it into this. And we could do it the other way. We could go from purple to colorless. That's fine. But it actually works better. Okay, if you do it the other way. So what happens is we're going to have the acid in here, clear and colorless, and we're going to use 20.0 mLs. Okay, it just seems more convenient. And generally we use something like 0.10 molar, 0.2 molar sodium hydroxide. Okay, so we can pick one of those. But what happens is, as we're doing this experiment, we have this colorless acid, right? And we add phenolphthalein. We add a few drops. So we have a little dropper bottle here. There you go. Looks like that. Little dropper of phenolphthalein. Learn how to spell that. Phenolphthalein. Phenolphthalein. That's how we say it. Right? But when you add this, it doesn't do anything. It still looks colorless, right? So we add a few drops of that stuff, but it still looks colorless. Okay? Then what happens is, as we're doing this experiment, though, we have to titrate by swirling this the whole time we do it, because we want to have a chemical reaction. We want to mix that up. So we're going to be swirling this the entire time. Okay? So what happens? All right, if we used, let's say 0.20 molar, and we used, let's say that we needed 14.2 mLs of the base, then the question is, what is the concentration of the acid? That's the problem we have before us. If we used this concentration here, 0.2, and we poured out 14 mLs between here and here, then how strong is that acid? So here's how the math works. The molarity of the acid, let's write it out, times its volume rather, is this. Okay, but we want to know what's the concentration of the acid. So we leave that there. Molarity of the acid equals, these guys go over here, and you divide by, right, that acid's going to go down here. Do you see how that ratio keeps showing up, this ratio of those? Now you can figure out, is it going to be a stronger acid or a weaker concentration rather? Okay, so you know this is 0.2, but you only needed 14 mLs to counteract 20 mLs. So this stuff must be stronger. Well, it must be stronger. Okay, so what happens is you take the ratio of those. Let's see what happens here. So the molarity of the base is 0.20 molar. And the volume of the base that we used was 14.2. Do we have something wrong here? We're looking for the molarity of the acid, right? So we have the base and its volume. Okay, let's see. Oh, it's weaker. Okay, that makes sense. So the volume of the base that we used was 14.2 mLs. The volume of the acid was 20 mLs, right? That ratio there is about 70%. In other words, this acid is 70% as strong. So let's do the math, okay? 14.2 divided by the 20. That number tells me it's 70% as strong, 71%, times the 0.2. So this is 0.142 molar. And by the way, that worked out pretty well, didn't it? Right? So that acid is 1.142 molar. Okay? So that's a simple idea of titrations, that we are adding a known concentration to an unknown concentration. But we should take a little closer look, though, at some of the vocabulary. All right? Let's make sure that we understand what's going on. Okay? First of all, the analyte, to analyze, right? That is a sample being tested. All right, so your analyte is a sample that's being tested. That would be the stuff sitting in the flask. Okay? The indicator is a chemical that has specific color properties. And in this case, it changes color based on pH. So that's going to be very important, and we can talk more about indicators later. Okay. The standard is the known solution that is in the buret. Right? And it's also known that the analyte is, by the way, the titrant. That's the stuff that gets tested. Okay? So those are some of the terms we use. The buret is just that long glass column. Then there's something called the end point, and that end point where there was a color change. Right? So we know to stop the titration when the clear colorless phenolphthalein turns magenta suddenly, then we call that the end point. But there's also something called the equivalence point. And that means where H plus is equal to OH minus. And they're pretty much the same. Not always. For reasons we'll get into maybe later, but there's something called the equivalence point. All right, so these are the basic ideas of titration, but we should make sure that we have all of the concepts here. All right, so what are we doing here? Titration is a process of finding the strength or the concentration of an unknown sample, but you need to have something that is known. And we use this buret because it's a very exact method, very precise glass tube here. So a couple drops will show up, and you pour out a couple drops and you'll have a very exact concentration here. Okay, you put the unknown in the flask. Okay, and every time that you add drips of the known stuff into the unknown, you're really turning them into water. Okay, but what happens is after they're all gone, then you have excess H plus, and if that's the case, then those are acidic conditions. But there's another way to do it, and that is what if we put the H plus here in this flask? There's the chemical called phenolphthalein. There's a whole bunch of chemicals that change colors based on acids and bases. And this one, called phenolphthalein, is colorless. This one's colorless, so that means that when I put it in here with acidic conditions, you can't see it. But we keep adding these hydroxides, and they make water, and then what? We have extra OH minus. And as soon as that happens, the whole thing turns magenta. Absolutely. And we stop the solution. We stop this titration, rather. Okay? So what happens? Now we can say, right, based on the numbers that we have, we can do some calculations like we've done before to determine how strong the unknown is. So in this situation, it turns out that our sample was 0.22 molar. Okay? So we did a second example here just to confirm, just to show you how titration actually happens. We add these chemicals in here and we swirl this the whole time to make sure we're reacting acids and bases. And again, pay attention closely to that ratio there because that's going to help us very easy. So our acid ended up being 0.142 molar. And finally, these are some of the common vocabulary words that we're going to use. Okay? Because as we do a titration, then you have to know what those terms mean. So that's the simple idea of titration.